As discussed in the Newton's laws video, Newton was able to describe the weight of an object as being F of g, the force due to gravity on Earth, as being mass times gravity, lowercase g being the acceleration that Galileo had calculated through his Leaning Tower of Pisa calculations for 9.8 meters per second squared. However, this is specific to Earth, and that's because we live on Earth, and Galileo was able to measure the acceleration. But Newton was asking the question is, what actually causes gravity? What is gravity at the heart of it? And what he came to define was the force between two masses as an attractive force, attractive only, no repulsion this time, and directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And so, in a more general terms, he was able to describe the fact that there is gravity that exists between all matter, not just us and the Earth. So in mathematical terms, he described the force of gravity, or the attraction, universal attraction, as being proportional to the product of the masses, m1 and m2, and inversely proportional to the radius between them. So you can imagine that if we were talking about u on Earth, this mass is u, and then the remainder of those terms are collected in the acceleration characteristic of Earth. But if we were looking at it in general sense, then we would say the force of attraction between u and the Earth would be the mass of u times the mass of Earth divided by the separation between u and the Earth, which in this case would be the radius of the Earth squared, right? And so you can imagine that in order to do any kind of calculations for figuring out weight prior to this, we would have had to know the mass of the Earth and the radius of Earth in order to calculate these things. Not only that, but also the proportionality constant. It wasn't until much later that a scientist named Henry Cavendish performed a series of experiments in order to measure the proportionality constant between two objects. Now, he couldn't do it between us and the Earth because we didn't know the mass of the Earth, so he instead used known values of lead spheres and related to how they would be pulled to each other based on a set distance. Through careful experimentation, he was able to determine the proportionality constant, which has now been dubbed G capital, as being the universal gravitational constant. In this case, his experiments yielded a gravitational constant of 6.67 times 10 to the negative 11th newtons times meters squared divided by kilograms squared. So that finalized the universal gravitation law as being G times the product of the masses divided by the radius of separation squared. So through this calculation and the proportionality constant for two known masses, what he was then able to do was use this proportionality constant and the known mass of any object, and then a calculated radius that had been measured in Europe, in order to calculate the mass of the Earth. This was the first time the mass of the Earth was calculated, was after Cavendish was able to determine the universal constant. This becomes very, very useful. You can imagine that calculating the force between two objects is weight on any other planet besides Earth. And so if you know the mass of a planet, then you can calculate the way objects would be affected on those particular planets. It is important to note that on Earth, this is relatable by saying that if you are comparing the force due to weight as this universal force, then simply your mass times the acceleration due to Earth would be equal to the proportionality constant times the mass of Earth divided by the radius of the Earth squared. And so again, these masses are common, and we understand that the acceleration on Earth is this proportionality constant based on the mass of the Earth and the radius of the Earth squared. Again, the acceleration on Earth is constant regardless of what the mass is, because the force scales directly with the acceleration and the mass scales inversely with the acceleration. And so no matter what the mass of an object on Earth is, its acceleration is dependent upon the Earth mass and the Earth's radius, and the characteristics of the physical device do not affect the acceleration. Nevertheless, Newton's universal gravitation law can be very useful for determining a number of characteristics of attraction between unknown masses out in space as well as on Earth.